Have you ever been watching an ice skater just totally mesmerized when they suddenly pull their arms in and accelerate into this incredible, fast blur? It seriously looks like magic, right? But it's not. It's actually one of the most beautiful principles in all of physics. So today, we're going to crack this puzzle wide open and figure out the secret behind the spin.
I mean, this is the big question. We've all seen it. The skater starts out, arms wide, spinning kind of gracefully, and then bam! They pull their arms in tight, and it's like they hit a hidden turbo button. They're suddenly spinning impossibly fast. So how? How do they do that? What invisible force are they tapping into?
Well, here's the cool part. The secret isn't some brand new, super complicated set of rules. Nope. It's actually based on stuff you already kind of know, the physics of how things move in a straight line. We just need to learn how to, translate that language into the world of rotation, the world of circles and spins. So think of this next part like we found a special physics decoder ring. We're going to take all these concepts we're comfortable with, like force and mass and momentum, and find their secret spinning twins. And once we do that, the skater's magic is going to make perfect sense.
Okay, so this right here, this is basically our Rosetta Stone for all things that spin. Everything on the left, which describes moving in a straight line, has a direct partner on the right. So regular velocity becomes angular velocity. That's the Greek letter omega. Force becomes torque, or tau. And for our puzzle, the two most important ones are right at the bottom. Mass becomes something called the moment of inertia, and momentum becomes angular momentum.
All right, let's zoom in on the two most important translations from our little decoder ring. We're talking about the spinning versions of force and mass. I promise you, if you get these two ideas, you've basically unlocked the entire secret of the ice skater. First up, let's talk about torque. It's actually really simple. You know how a force is just a push or a pull that makes something speed up? Well, a torque is just a twist that makes something start spinning, or spin faster. Think about opening a heavy door. You don't just push on it anywhere, right? You push the handle, which is far from the hinges, to create a twisting force. That's torque. Okay, now for the big one. This is the key, moment of inertia. We all get that mass is how hard it is to push something. A bowling ball is harder to push than a tennis ball. Easy. Well, moment of inertia is how hard it is to spin something. And here's the kicker. It's not just about how much stuff there is. It's also about where that stuff is located. This is the crucial takeaway right here. The more you spread an object's mass out, away from its center of spin, the harder it is to get it spinning. Just picture trying to spin a barbell. If the heavy weights are clamped right in the middle, it's pretty easy. But if you slide those weights to the very ends of the bar, whoa, it's suddenly way, way harder to spin. That's a high moment of inertia. Just keep that image in your head. And just like that, we have all the pieces on the board. We've got torque, the twisting force, and we've got moment of inertia, the resistance to spinning. With just those two tools, we are ready to solve the puzzle of the ice skater once and for all. And the entire solution boils down to this one beautiful, powerful law of the universe, the conservation of angular momentum. You've heard of regular momentum, kind of the quantity of motion, right? Well, angular momentum is just the quantity of rotation. And this law says something amazing. Unless some outside twist and external torque messes with it, the total amount of spin in a system never changes. It has to stay the same. So how do we actually measure this quantity of rotation? Well, the formula is super elegant. Angular momentum, which we call L, is just the moment of inertia, I, multiplied by the angular velocity, or spin speed, omega. That's it. L equals I times omega. Okay, here we go. Let's put it all together. Step 1. The skater starts her spin with her arms stretched way out. Her mass, her stuff, is spread far from her center. So, as we just learned, her moment of inertia, I, is really high. Step 2. She pulls her arms in tight. By bringing all that mass close to her body, she massively lowers her moment of inertia. But remember that cosmic law. Her total angular momentum, L, has to stay the same. And boom! There it is. If L has to stay constant, and she just made I, the inertia part, way smaller, the only way for the math to work, for the universe to stay in balance, is for the other part, omega, her spin speed, to shoot way up. It's not magic at all. It's this beautiful trade-off. She trades her resistance to spin for raw speed. And honestly, this is so much bigger than just a cool trick you see at the Olympics. This law, the conservation of angular momentum, is a fundamental rule that shapes literally everything in the universe, from a tiny toy on your desk to the biggest galaxies in the night sky.
It's why a spinning top seems to defy gravity. It's why planets keep spinning on their axes and orbiting the sun for billions of years. It's even how stars are born. A giant, slow-drifting cloud of gas in space starts to collapse under its own gravity. As it gets smaller, its moment of inertia drops, and it's forced to spin faster and faster until it ignites into a star. It's the exact same physics as a diver tucking into a tight ball to do more flips before they hit the water. It's everywhere.
So the next time you see an ice skater pull off that incredible move, you won't just see a trick. You'll see a beautiful demonstration of a law that builds stars and holds solar systems together. And so my question for you is, now that you know what you're looking for, where else are you going to see this amazing principle